Ranking resonance structures is important because we need to be able to tell which structures contribute more to the resonance hybrid. So the resonance hybrid we'll talk about more in the next video, but that's the way the molecule actually looks. So these individual resonance structures all kind of come together in that resonance hybrid. And to figure out which structures are more important for that resonance hybrid and which contribute more and therefore the molecule looks more like those structures, we have a set of rules for ranking resonance structures based on stability of the structure. First and most important rule is that all the atoms have full octets, then least amount of charges on the structure, so these are formal charges. Then we're looking for if we have any negative charges on the molecule, that they should be on the more electronegative atoms. And if we have positive charges, they should be on less electronegative atoms. And the rules 4 and 5 apply if we have more than one charge on the molecule. We want maximum separation for if those charges are similar. So having two negative charges on the molecule, we want them as far apart as possible, or two positives. Having a minimum separation of opposite charges is also the very last rule. So if we have a positive and negative, we want them as close together as possible on the structure. So we're going to follow these rules from number 1 down to number 5. And the most important is the first rule. So these are the resonance structures that we've drawn out for the previous examples. We're going to go ahead and rank them. So the first thing we're going to look at is which structures have the atoms that have all octets. And so when we're looking at these structures, one of the things that we know doesn't have an octet is a positively charged carbon. We have that in these three structures, and so likely those ones are already violating that rule. Let's take a look at this first one and this third one. So the first one has all neutral atoms, likely that all those atoms do have octets. So automatically we can say this one is better than any of these three. For the structure on the right-hand side, we do have this oxygen that's positively charged, but it does have an octet. So unlike carbon, when carbon is positively charged, what led to it being positively charged was, pulling those electrons away from the carbon, and so it's left without an octet. But because this oxygen actually ended up donating and sharing electrons, that's how it became positive. And so it actually still does have an octet. We have these two electrons here, two from this bond, that would make 4 total, two from this bond, 6 total, and then two from the bond to the H. So we actually do have 8 total electrons around that oxygen, and then all the other atoms also have octets in that molecule. So automatically, this structure and this structure are better than the other three. So let's continue and look at the second rule, which is the least amount of charges on the structure. So with this first structure and the third one, we're trying to figure out which one's the most important at this point. We have formal charges on the third one, so we have a negative and a positive. We don't have any formal charges on the first one, and so automatically that makes the first one the best structure. And so that's the most like what that molecule is going to look like, is that first structure. For the other one then, because it does have all the atoms that do have octets in that structure, that's going to be number 2. Now we have to decide between the other three, which ones are going to come next. So then we start going down our list because we already said that they don't have full octets. Let's re-examine this second rule because this might help differentiate them at this point. Least amount of charges on the structure. We're taking a look at these three that are left, and we have a positive and a negative on each structure, and so they each have the same amount of charges. Negative charge on more electronegative atoms and vice versa. So this one, positive charge, is on a carbon in all cases, and the negative's always on the oxygen. So that doesn't help us differentiate. Have maximum separation of similar charges. We actually have two opposite charges only on the molecule, and so this rule also does not apply. But if we take a look at that last rule, that's going to help us separate out all the other structures because we want these opposite charges, so the positive and negative, to be as close together as possible on the molecule. We see that in the first one, we have the negative and positive right next to each other, so that's looking good for that structure. They become farther apart in the second one because we have two carbon atoms between the negative and the positive. And then in the last structure, you even get them farther apart because we have 4 carbon atoms between the negative and the positive. And so these structures are going to be ranked with number 3 now, being the one where the positive and negative charge are closer together. Then, as they get farther apart, the structures become less and less important. So our ranking of the structures goes like this. So that means that that very last structure, it doesn't contribute overly a lot to the resonance hybrid. Let's take a look at the structures from the example. If you want to pause the video and try to rank these based on the rules that we have below, that would be a great idea. We're just going to go right into this. So if you're going to pause it now, try to figure out which structures are ranked which. For our rules, so first thing for A we're looking at is, do all the atoms have full octets? And in fact, we do on every single structure. All of the atoms do have octets because we have negatively charged oxygen. We can see all of those electrons and then the two in that bond. A negatively charged carbon does have an octet, so positively charged does not. Negatively charged does because there's an H we're not showing there. So there's 2 electrons from each of those 3 bonds, and these two make 8. And so all of these structures do have full octets. The next thing we look at is least amount of charges. We have a negative on every single structure, so they're still tied. Then we go to negative charges on more electronegative atoms and vice versa. We have a negative charge on oxygen in the first structure and then a carbon in the other 2 structures. Oxygen is more electronegative than carbon, and so automatically that makes this structure 1 because that's a better structure because that negative is on the more electronegative atom. So that's number 1. The other 2 are still tied because they have the negative on a carbon. And then the last 2 rules don't apply to these structures because we only have the 1 charge. So there's no max or minimum separation because there's only 1 charge on the molecule. So these ones are actually going to be tied at 2. So it is possible to have resonance structures that are contributing equally. Not as much as the first one, but they contribute equally in second. For the last example, we're going to go through, we see that do all atoms have full octets? We actually have this positively charged carbon, so we don't have an octet on the first, second, or third structure, so actually none of them have full octets. Least amount of charges, we have 2 positives on every single structure. Negative charge on more electronegative atoms. We don't have negative charge, but positive on the less electronegative atoms. But this nitrogen has a positive in every single structure, and a carbon has a positive in every single structure. So that's still not helping us. Rule number 4, have the maximum separation of similar charges. With this one, we have similar charges, so this is going to apply. They're 2 carbons, apart in this structure. They're also 2 carbons apart in this structure, but they're right next to each other in the last structure. So that means that this last structure is actually worse than these other 2. And so we know that this one's going to be last. There's no more rules that are really going to help us to differentiate anything because we don't have opposite charges in the molecule. And so automatically we know that these are going to be tied for being the best structures, and the one with the positive charges right next to each other is going to be the last and the least contributor. And we're going to see structures like this in organic chemistry too come into play and help us influence, what is going to be a major product in a reaction. So we're going to see that this structure is really bad in some of the pathways. So just kind of a little foreshadowing there of what we're going to end up seeing. So that's kind of why it's important to be able to rank the resonance structures because they can help us with figuring out reactivity.